Okay, hello everyone. Uh, so today and next week we will still have online classes as scheduled, and your midterm will be postponed to next Thursday, and hopefully there's nothing, no other cases, and we can return to offline class and return back to the class and continue our study. Okay, so maybe we can start with I will just take some review. Okay, this is the example that we have done. Okay. We will go back to here, but let me just review what we have done in chapter 7. So basically, we are looking at the first law of thermodynamics. Okay, so can you see my note clearly? Is there any delay? I think smooth, right? It's quite smooth, right? Can you see in your screen? Okay, smooth. Thank you. Okay, so first law of thermodynamics. Uh, we mentioned last time we mentioned that we have a process of energy transfer, right? And we can transfer in terms of heat or heat. We can transfer in terms of work. Okay. Now, to understand how this heat and work how they are connecting and how they are relevant in the process, then if we are having a system, okay, and the system is doing work, it means that the system will lose its heat, and if the work done to a system, it will gain heat. Now from this process, work and heat transferred into or out of system. This represents the the change in its internal energy. So this is what is actually referred to. So we can say that the internal energy, okay, this will be the total kinetic and potential of all molecules in the system. Well, you can think as in the molecular levels that your atoms is always move, like in your body it's always move, okay? It always vibrate, it always move. And from this idea we know that we can refer the internal energy as change in work and change in heat. And all of this is our interpretation or our perspective on first law of thermodynamics. Okay. If you're still confused on how this works, the system and when the system doing work or work done to the system, we can say that let me write, the heat can be positive, can be negative. This will be heat, or maybe heat, heat transferred to or into the system. And negative means that heat transferred out of the system. Well, you could also include surroundings or environments to help you to imagine, but I think into and out of, I think also, I think much simpler. And work, positive, negative. So work done by the system and work done on the system. And we can write down the internal energy. The change is and you can also relate this process, the first law of thermodynamics, with um, the conservation of energy, right? It's relate, describe the conservation energy. And I think you also have learned that we can also represent work as integrations of the and we will have some process. Okay. Let me just write, and maybe you can uh, review later. Okay. I think you can review on your physics or chemistry notes. So we have the isopolometric, we have the isothermal, we have the isobaric, we have the adiabatic that we already also mentioned in our course. And this process describes the process in its name. Okay. Isopolymeric means the volume will be at a constant. Isothermal means the temperature. Isobaric will be the pressure, and so on and so forth. And adiabatic means that it's isolated, so the heat is zero because it's perfectly insulated. And perhaps, although it's not mentioned in your textbook, maybe let me mention uh, the second law of thermodynamics. I think it will be related to the next part of our sections, but let me mention here so that we are connecting this first law to the second law. So the second law I will just write the essentials and emphasize which are rather sensitive to our force. So this means heat will spontaneously, and this is important to say, spontaneously flow from let me just write from warmer to colder. Although this is a simplification, but I think this is the best way to describe. And we are going to describe this in terms of entropy, or we call this the order of chaos. Order of chaos, or the official word is the disorder of the system, inherent disorder of the system. So the more disordered or chaos then the higher the entropy. And by doing this, from these definitions, this will at least, okay, if you look on the phase, the gas, liquid, and solid, the entropy will be highest at the gas phase. Okay, so the phase will be our discussion later part, I think in chapter 8. Okay? But I hope you get the at least the description, the basic description on the entropy. Okay, I think we can get on the notes for the next part. Okay, perhaps any questions? If you feel the notes maybe have some trouble, you can write in the chat box, or if you have any questions, you can write in the chat box. Okay. So first is the first law of thermodynamics, which we are going to include heat and work and how they are flowing, basically, how they are going to lose heat, gain heat, how we can define them in terms of positive, negative signs in these equations. And of course, the equation for the whole thing, for the energy balance, we already mentioned in the last part of our lecture, which is this one, okay, this part. Or actually, you can remember this. Okay, this is without energy, kinetics, and potential. But if you have, then you can mention here as well. Okay, now the next part is the energy balance on open system at steady state. So open system, as I think we mentioned in the last class, if you have closed system, means that no mass transfer. So if we talk about open system, then we can say that the mass crossing or transferred its boundaries. So how the mass and why the mass is getting over to the or crossing the boundary. So to define those processes, then we need to have our work must be done on the system to push mass. So work and system and pushing the mass. So we are going to look on more about the work, okay, in the first section on this open system. We will have net of work, net of work done maybe it's not complete yet. Let me then complete this sentence. And work is done on surrounding by mass that emerge. And both sentences, they need to be involved in our balance. Okay, and then the net of work done by open system on its surroundings you can write as work. Then we have the shaft work plus the low work. The shaft work done by the fluid, by the process fluid on moving parts. Within the system. And this is the flow work done by the fluid at the system outlet minus the rate of work done on the fluid at system inlet. It's actually system outlet minus system inlet work. If you would like to analyze and describe more, you can describe in a flow chart. Okay. Let me go here first. So we have a process unit have the volumetric flow rate, the inlet, we have some pressure in there. This is sigma cube, this is Newton per meter squared. This is the volumetric outlet. Okay. So the fluid enters. So fluid enters. And fluid exits here. The fluid that enters has work done on it has work done on by fluid by the fluid behind. While the fluid leaving the fluid leaving the system performs work on surroundings. And this is the rate. The rate. So the flow work will be, and I think this is pretty much in intuitions it should be relatable, but I don't think it's a problem. So yeah, this is just an example, and if you have one streamline, okay. So if you have more, so if more streamline, then each stream must be some. Which one is outlet? Which one is inlet? Okay, I think it's not that complicated. Yeah, as long as you understand the flow work means that the system on the outlet minus the inlet. Okay. Now the next part will be we will discuss the enthalpy. But before knowing what enthalpy is, first let me describe you the specific property. So what is a specific property? Specific property means that it has intensive quality. What does this mean? It means that you have an extensive or intensive or the extensive would be better to say extensive property. For example, the flow rate divided by the total of process material. As an example, we can say the specific volume. If we write specific volume is 1 centimeter cube over gram, perhaps we have conditions that the volume we have 200 centimeter cube, and we have the mass 200 gram. If we have mass flow rate 100, maybe like clearly 100 kilogram per minute, and volumetric flow rate is 150. Specific volume will be 1.5 liter per kilogram. Okay, so that's how we define the specific volume. So specific volume is it's intensive. It's intensive. Not quality. Sorry, why am I writing quality? Should be quantity. It is intensive quantity that is supposed to be written as we have an extensive and divided by the total of the process material. And sometimes we are writing this, for example, the specific volume. The volume, you know, this is the volume. The specific volume, we have something up there, apostrophe. So this means it denotes the specific property. And if we have another one, for example, the U, this will denote the specific internal energy, right? Okay. Okay, we can write this internal energy. I may write in the new page. We can write the internal energy, or we can write the internal energy as in joule. We have the mass and we have this specific. So basically, all the specific terms, that is, we are having a specific property, means that your property and it will have the total material process, the total material, which usually denotes by its mass. So we can rewrite the property itself as mass multiplied by its specific property. In our case here, we have the internal energy equal mass multiplied with the uh, specific internal energy. And similarly, if you are thinking on a flow rate, and that is because we are dealing with more process in the future, we can deal with this the flow rate, and this should be equally the same. So your specific property can be included as well. And we can write down this. We call this H the enthalpy. And what is enthalpy? Let me write the equation first. So we have the internal energy, right? And this is plus PV. What is PV? Pressure and specific volume. What does this symbolize? This symbolizes actually work that can be evaluated. So you can relate this to what we have written before, that we have this. Okay. And you can write this as this actually synchronized with this the enthalpy. So here is pressure. This is specific internal energy. This is the specific volume. And this is defined this specific enthalpy. Okay. Uh, Let me go by adding some notes for you, which is not really mentioned in the textbook. Uh, Heat and work. These two are pathway dependent. For example, if you are dealing with kinematics problem in physics, you have a box that is going down this line here. You have some force, or maybe just having some movement in that directions, and it has some frictions on the ground. It has friction, and you compare with the other or maybe to make it more logical, not frictions. Maybe this is a vehicle, okay, and then you are uh, pressing the brake. Okay, let's just pressing the brake. So inside this is a vehicle, a car probably, and you have the other car. Okay, I'll draw here. That is just moving the same directions, and it's without brake. So without brake. So this without brake. Of course, without brake, it's going to be they are going to accelerate very fast, right? But if we compare these two, the change of energy is the same, right? If you look on some part of the conditions, maybe we can think on the difference on the kinetics. If we look on the total, the energy of the change of energy is still the same. The first law of thermodynamics, if we look on the energy perspective, they are both the same. So we can say that the change of energy still same. And then we can say that in terms of energy, okay, the change of energy, they are independent pathway. So what does pathway mean? So pathway means they need to have some steps. Okay? They need to have some process. And if I say independent, means that we are on the thing start and finish. So that is, or we call this a state function. We call this a state function. Based on loss and gain of heat in chemical reaction. Later we will deal with this. So what does this relate to our enthalpy? So basically, if we have some enthalpy, have internal energy plus P, that means that this enthalpy is not very clear because we can't really measure. Okay, we can't really measure. But since its energy, and it can be described in state function, then we are just dealing with the start and finish, or we can dealing with the delta of the energy. Okay, I hope that is clear for you. Okay. So from here, we can really going to develop that we have the delta of the enthalpy, we have the heat itself, and then we have the work, and we have some delta that is having some pressure and volume. And why I took this delta for both cases here, because sometimes the pressure can be a constant, sometimes the volume can be a constant. Let's say the pressure is constant, then we can write yeah. Okay, so we can look here. We can see that we may have the only work done in the system. The work that the pressure does to change the volume. So we will have the pressure volume work, in which described into this formula. So the work will be described as this minus P delta V plus P delta V, or we can just say that the change of enthalpy will be equal to Q. This terms, okay, if you remember, I think in physics, yeah, the change in enthalpy will be, we can approximate this by the heat gain or heat loss by the system. So increase or gain is resulting or results on output of work by the system. The loss in internal energy described by the negative sign. And if you're looking or thinking in the microscopic scale, you can think the atoms and molecules, they are releasing energy or they are gaining energy. Okay. And from this, the delta H, the state function, we can relate this to the Hess law that you have learned in chemistry. So this means that the total enthalpy change for reaction doesn't depend on the pathway takes. It depends only to its initial and final states. Okay. Okay, now why I'm doing this, okay, to give you some this context. Okay. This is to understand what we are dealing with. Okay. So basically, because we cannot really measure the enthalpy as in uh, in the in the numbers, or we cannot really find, but we are but it's there. The enthalpy is there. So how to visualize this enthalpy? So we can look on how it is on the initial state and the final state. And we can simply put the enthalpy as its delta. Okay, and all of these notes you can check out on your physics and chemistry notes. Okay, wait for a moment. Okay, sorry. Okay, so you can check your notes on physics or chemistry about this energy and how it relates. And at least in our course, in the energy balance part, we will deal on the enthalpy chain, um, and also the Hess law. Later we will deal with the Hess law. So I mentioned at the very beginning here to prepare for some works that we are going uh, to to work on in the future. Okay. So this is actually from this part here, from this notes here. This is my additional notes to help you get into the context, okay, for the enthalpy. So you are not really going far away from what we have to learn in terms of basic engineering courses. Because basically, if you learn sciences, engineering, they have the basics, the basic concept, and I hope you can relate your works, okay, in every course you are dealing with the other courses as well. Okay. Yeah, let me go back to what we have here, the enthalpy, and with the first law of thermodynamics. Okay, with the first law of thermodynamics, let's go back. we know that input should be equal with the output. So input signifies the total rate of kinetic energy, potential energy, and internal energy, or and output, of course, its total rate of energy transport by output streams. Plus rate of work. So if E, J, and it's a flowing energy, this is rate of energy transport. J means the integer. It can be 1, 2, 3. How many streams you have? By J input or output stream of process, and the heat and the work, they both are rates of flow heat. This is maybe this better, and this is work on the process. We can write down that Q plus W plus sum of the energy from the input streams this is equal to, this is output, and we can write down in terms of, this is output minus input equal the heat plus work. And we can design the energy for input or output. If you have the kinetics, potentials, and internal energy, we can write down and since we have learned on a specific property, then to make it more concise and precise, we can write down the flow in terms of the specific property. The kinetic, we will describe that it has also mass flow rate. And potential. And now from here, we can write down the energy. I will factorize the mass outside. This will be specific internal energy, the velocity, and gravity, and the height. And let me denote this. Okay, so that's our energy. The rate of energy, to be precise, rate of energy transport into the system or out of the system. Okay. Okay, this is the part for energy. Now we still have part for at least for work, because we have described work can be in terms of we have shaft work, flow work. Okay. We need to also mention all of the information in these equations. So maybe right here that the work flow or flow work, this will equal and we can define the flow as in the specific property and using the same mass so that later on we can connect this mass with the energy part. And we'll write a little bit left. Sorry. So now we have total work as the shaft work plus the flow in terms of the summations. So we are going to change all the energy and work inside this first equation we get. Okay. So maybe this one, this two, and this three. So we combine all equations, then continue here. Okay, let me write on the new page. So sum is having mass, internal energy plus this output streams minus Now let me just copy this. This is input. And this will be equal to Q plus work the shaft work, sorry, the shaft work. So this is from the flow, okay, from the flow. This is flow, right? Okay, flow. Let me check. Yeah, just to make sure. Okay. So this is from the workflow. Okay. So this is not plus, it should be minus. Okay, now we know also that we have approach for enthalpy as this, right? So we have here, so we can rewrite as enthalpy. So we can write the sum and internal energy and VP become the enthalpy plus copy this equal heat and the shaft work. So we have the difference output input for specific enthalpy, for kinetics, and for potential. Okay, so we can define all this difference with terms delta. So delta of H will be and delta of kinetic energy and potential. So we can rewrite all those terms into delta So this is stating net of rate energy which transferred to a system as heat and or shaft work. Will be equal to difference between the rates enthalpy, kinetics, potential is transported into and out of system. So I believe this is essentials for chapter 7. So please remember this one. And if we have the mass in, mass out equal m, then we can simplify the delta of enthalpy as m and the difference on the specific. Or we can write this as and if specific enthalpy specific variable has the same value like specific enthalpy, we can write down as then if the mass is the same, then we'll see that this will be 0. Okay. Any question? Okay. I believe enthalpy is not the first. It's not the first. This is not the first time you heard the word enthalpy. It should have the same meaning for um, in other courses, especially the basic course, as in physics or chemistry. You learn also the enthalpy, right? And you also denote the enthalpy as the delta. delta H, not just H. Or maybe specific enthalpy. That is something that usually we may use. Okay. Okay, next sections. We go put the uh, okay, 500 kilograms per hour of steam drives a turbine. Steam enters the turbine at 44 atmosphere, so that's the pressure, and 450 degrees Celsius, the temperature, at a linear velocity of 60 meters per second. So it has some velocity and lives at a point 5 meter below the turbine inlet at atmospheric pressure and a velocity of 360. So it has a difference in terms of pressure and velocity. And turbine delivers shaft work at a rate of 70 kilowatts, and the heat loss estimated to be 10 to the power 4 kilocalorie per hour. Calculate the specific enthalpy change associated with the process. So I think as previously mentioned in the previous chapters as well, like from Professor Astor, I believe one of the important things in material and energy balance is not just calculating the numbers, but to draw the flowchart. And that's actually the objective of the course. So you need to be able to identify the process, and then by identify it means that you need to be well to be aware of uh, what the question is, or how you can develop the process from the problems. For example, here we have a turbine, um, but we don't really need to draw like the details, but we just need to make sure that all the essentials are captured in a single graph. So what does it mean? Uh, if we draw a system, it says that 500 kilograms per hour. So we have the mass, right? The flow of the mass. We have flowing here. we have 44 atmosphere entering the turbine, and then 450 and a linear velocity of 60 meters per second. Okay, and then lives at a point 5 meters below. So 5 meters below, maybe 5 meters. And leaves the turbine. So this is saying, it says that at atmospheric pressure, so 1 atmosphere, and velocity of 360 meters per second. Okay. It doesn't say anything about the mass, but should be same mass for the P. Oh, the work for the shaft work is 70. Not having any load, so it should be 70 kilowatts. And we have the heat loss, the Q, the heat. Okay. Oh, because it's heat loss, let me describe this in negative. Heat loss. This is pressure, mass flow, temperature, velocity. So from the equations that we have described at here, so we are going to work on to find the enthalpy. So enthalpy will be described as this. Okay. So what we are going to do, we are going to evaluate the kinetics and potential. So kinetics. The delta means that we have two velocity that we need to subtract. And all the units, we have hour, we have second, we need to set up conversions. So set up the conversions. This become kilogram per second, 0.139. And all the units we need to describe as well. 360 squared minus 60 squared divided by x squared. The conversion, converting to watts. So convert and get the delta of the kinetics will be 8.75 kilowatts. Similarly, for the potential, gravity is 9.81 Newton per kilogram. And then the height difference is -5. It should be 0 minus 5, right? And then multiply with the 1 kilowatt. So we need to exchange all to the kilowatt. The work shaft is 70 kilowatt. Oh, the heat we need to remove the hour. So we need to convert to watt. This will become 11.6 kilowatt. And the enthalpy Q minus this will equal 90.3 kilowatts. So we have the delta for kinetics, potential, the heat, shaft work, the enthalpy we have. Oh, we need to calculate the specific enthalpy. So specific enthalpy can be calculated through kilojoule per kilogram. Okay. Any questions first? Okay. Okay, I think not really that difficult. So this is, I think, at least essential. So essentials part is drawing the schematics and then involving the equations. So if you are able to identify the questions from the problem set, I believe that is first step or half part of your result or solutions. And if this requires, at least for the schematics, will be regarded as 30 to 40% of the total work. Okay? Because if you are able to continue from this schematics, yeah. The block diagram is the most difficult. Yeah, I think so too. Eventually, if you are maybe missing out the point in the questions, then you are not able to translate the the questions to or the information to diagram smoothly. So first, you need to be able to understand at least uh, not just only reading carefully, but you need to understand the terms. What is exactly the question wants or what is the solution that should be written. So you need to actually, like, for example, uh, it's asking the specific enthalpy change. So it should be specific enthalpy, not just an enthalpy. Okay. So I also miss out that part. Uh, and I think this example here shows you it's more on uh, really not that complicated part of the question. After we finish this chapter 7, I think I can go for evaluating um, or exercising more problems with you, and I hope we can have time to do that. If not, then I will make into one video, but uh, I want you to also try, and in that video I will not show all the calculations. I will just showing you the steps, and you need to at least try that steps and try to calculate by yourself to make sure or to confirm that it is correct. And if you have something like problem when you're calculating, you can let me know in which part of that problem. Okay. Okay, so I think this will be the last session for today. So we will have um, the reference state. Okay, the reference state. So the reference state and states property. State property. As I mentioned before, that the age, specifically the specific enthalpy, not possible to be measured, but we can measure through this the delta, which means that if we know some reference, we can always compare from what the unknown to the reference, as in the delta. And we say that it is called the reference state. This is a convenient way to measure the change in internal energy and enthalpy. So basically what reference state means is we are going to choosing temperature, pressure, the state of aggregation, state, and list the internal energy, specific enthalpy for changes from this state to other states. Okay, suppose we are going to see the change from 0 degree of Celsius and 1 atmosphere to some other state. In the example here, we have the carbon monoxide gas, 0 degrees Celsius, 1 atmosphere. You will get this is gas, the temperature change, and pressure also change. And based on the example, it says that this will be the specific enthalpy change is 2919 joule per mole, and the other example here, from the same state property, we will go to a different one. It goes to 500 degrees Celsius and 1 atmosphere. So only the temperature changing. Based on the table we have, this will relate to 15,060 joule per mole. So we can construct a table that when the temperature change, the specific enthalpy also change. So we may assign this 0, or the specific enthalpy at 0, as a reference state. And then we can assign the temperature change, and then this will be the specific enthalpy, and this will be also specific enthalpy. Okay. So how does we can get this 0 to 919, 15,000? This is from the delta, from the delta, and we set the reference state for the 0. We set that, and based on our understanding, then we can get to know the specific enthalpy for other temperature. And again, this specific enthalpy is not the absolute value of the specific enthalpy. It is our approach with the reference state. So it should be, so the number should be relatives to the reference state. Okay, I hope it's clear for reference state. And as not a homework, but please look upon, let me set this to resize this a little bit smaller. Please check the tables P5 to P7 in your textbook, if you have the textbook. If not, then you can ask your friend to scan or take photos. Please check the tables. This will be related to the steam table. And in the book, you will have all the reference you need for steam tables. At least on our course. This will be enough. And my suggestions is to prepare all the appendix. Prepare all the appendix in one bundling, like a small book. Okay. So whenever we have a quiz or exam or a final exam, you will using those table. Okay. And my suggestion, just copy all the table at your it's on way back in it's behind it's a back side of your book. So please copy that, make it into a bundle, and it's just for preparations. Okay, and you can check the tables and look upon the what does it mean, okay? And you will see that there will be some column saying that which one is the pressure, the specific volumes, internal energy, specific enthalpies. Okay, so at least learn how to read them. I think they mention how to read them like in the very first sentence, I believe. How to read those tables. And you need to differentiate what table B5 means and compare with B6 and B7. That will be related to uh, the saturated steam and super saturated. So B5, B6 is saturated steam, B7 is superheated steam. Okay. B5, B6. So whenever you heard superheated terms, then it will relate it to the B7. Okay. Okay. Uh, I will end up until here, but before we finish the class, I would like to have a feedback. Okay. I would have a feedback and to know whether uh, you are having um, good understanding on this chapter or not. If you haven't scanned the QR code, you can scan. Okay. Okay, I will go here. So scan again. Yeah, this session is recorded there. Don't worry. I already record. So wait for at least 30 minutes to 1 hour and it will be uploaded to the system. Yeah, you can always check the recording. Okay? And also later I will also add um, more videos. I think next week I will add more videos. Okay. And uh, you can use your real name or for playing a game. For playing a game. So you can use real name later. Okay. So I hope you're ready. Okay. If not, you can use um, the code that is on the screen. You can go to the menti.com and use the code. Okay. So question number 1, I will consider this as participation in class. Okay? So okay, hopefully for 6, 7 students. Okay. Okay. We'll wait for a few seconds more. You can use the website doranmenti.com and use the code, the number code that you can see from the screen above the above sentence. So 45495572. Okay, let's start. We have only a few seconds. Answer. True or false? Okay, okay. I think it's too easy. Okay, I hope you're writing your real name so that I can consider as a bonus point. Okay. Okay, number two. It doesn't have any calculation, so you just look on the screen and which are correct, A or B. Okay, okay, three students correct. Yeah, I hope you can change your name. I think you can change your name. You, what's your, okay. You need to type in, need to type in. I give you 40 seconds. Okay, Darren Drama Creation. Okay, yeah, okay, I think a lot of you get correct answer. Okay, Brian getting the top, the top, getting on the top. Okay, so supposed to be last questions, but not last slide. Okay, who is the winner? Yeah, Darren ran out of time. Yeah, you need to aware of the time. Be aware of the time. Okay, only 30 seconds. Okay, which one is the correct one? The true. Which statement is true? 19, 18, 17, 16, 15, 14, 13, 12, 11. 5, 4, 3, 2, 1. Ah, okay. No one getting correct. Okay, anyhow. then it's right. You get uh, win the game. Okay. Just a survey. Do you like this game? You can punch out the button. Yeah, Muse. What's your name in the game? What's your name in the game, Muse? So I will try my best to involve the game. Okay, okay, okay. Okay, so yeah, see you next next week. Okay, see you next week, and I try my best to getting involved in some kind of this activity. So see you later. Okay, bye everyone. Thank you for joining. Yeah, bye bye.